Second approach is very interesting, called software lock. Software lock. In like a 2 slide back, I told you that with the ordinary read and write instructions, it is impossible to achieve the mutual exclusion. That's actually incorrect. Some clever people found a complicated algorithm that use ordinary read and write operation, but implement the mutual exclusion. We call such algorithm software lock, because people call this as a software lock because it does not get any help from the computer architecture. So it's purely implemented with the ordinary architecture with the algorithm. So people call it as a software lock. And there are some algorithm. So let's check this algorithm first. This is a famous software lock algorithm called Peterson algorithm. A bit complicated, but check this together. So we have a flag variable. Flag variable indicate whether flag variable should exist as the number of the thread that involve in the same critical section. So if there are 2 threads, then there should be 2 flags, and 3 threads, there should be 3 flags. Anyway, and the flag variable will indicate whether a thread have a willingness to enter the critical section at the moment or not. And turn variable will indicate which thread is a turn to enter the critical section at the moment. And then initially, so in this example, this is the code for Peter's algorithm of the 2-thread. So this is the 2-thread version. Okay. So initially, it initialized the flag for each thread to be 0, because initially no thread have a willingness to enter the critical section. And then set the turn to a 0, and turn. Here we assume that 2 threads are named as a thread 0 and thread 1. So if the turn is initialized as 0, it means that initially the turn goes to the thread 0. It's a bit weird, but let's see how it is implemented in detail for the remaining operation. Okay. So log operation, what it does is that since this log operation, it first self-declare the caller's willingness to enter the log. So here we have a special variable called self, which return the thread ID. In this case, it will be 0 or 1. If it is 0, it means thread 0, and if it is 1, it means it's a thread number 1. Flag self being 1 to declare that, yeah, these threads have a willingness to enter the critical section. And then what? This is interesting. And then what? What it does is that it set up the turn to 1 minus self. What it means? Interestingly, it defined the turn into the other ones. So I say that I'm willing to enter the critical section, and then it voluntarily yield the chance to the other one. So I want to use, yeah, so for example, I want to use this resource, declare that, and then what? To the other one, say, this is a very humble action that, why don't you use this resource first? So it just set up the turn into the other ones, and then what? Wait until, and then what? Wait until the other one's flag to be 0. So wait until the other one have a no willingness to use this resource, or what? Turn come back to itself. So I just read this condition in negative manner. So this one wait, this one fall into wait if flag of the others is 1 mismatch. If the other one also have a willingness to use this resource, it's just a wait. and other one have a willingness to use the resource, and turn is on the other one, then it should wait. But if this condition is not, it pass on this blocking condition. And now at this moment, the current thread is holding the lock. This is complicated, but if you carefully write down all different scenarios of this algorithm, then you will find that, this logic makes sense. This logic makes sense. So for example, if two threads are executing the same locking operation, pretty much the same time, then first one, both of them will declare their willingness, and then what? Passing the turn to each other, then only one of them will have a turn value set to be self, then that one would execute the code and moving on. But if only one of them is executing the log operation, then what will happen? Then it first declare the flag variable, define the flag variable to declare the willingness, and then give a turn to the other one. But since the other one have no willingness to that, the current thread can hold the log, escape from this looping and pass on to hold the log. Interestingly, this algorithm works very correctly. Then why don't we just use this algorithm? Why don't we just use this algorithm? But there's some issue related to this type of the algorithm. First one is that, it's nicely working and it looks not that complicated for only 2-thread version. But if it should involve a 3-thread, 4-thread, and if it needs to generalize this algorithm becomes super complicated and also super inefficient. There are too many checking and too many waiting, looping, working. So this is a not really scalable solution. But we might think about this for like a 2-thread version. Yeah, so for example, if you're using very old computer architecture, like you're using like a 4-bit MCU, and you need to implement some form of the threading, this might be a solution. But if it is not such a cases, this one is not a good idea. This one is surely have no benefit in implementing the log operation. Second issue is that I briefly told you that, even if there is a global variable in most of the computer architecture, if one thread is updating a global variable, such update is not immediately visible to the other thread due to the cache effect. And then I told you that for efficiency reason, multiprocessor architecture intentionally allow cache not to be consistent with the main memory for temporal time period. So for many computer architecture, this type of the algorithm hardly works because update on the global variables are not visible to each other. They can enforce immediate update on a memory, but if it is going that way, algorithm becomes far less efficient because immediate update, synchronous update between the architectures and memory reduce the parallelism of the multi-core architecture severely. So that is not a good solution. So software log also exists as a theoretical idea to show that synchronization can be somewhat possible even without extra help from the computer architecture level. Okay, have any question here? This is an interesting algorithm, and Peterson algorithm is the one famous one, and another one is Decker's algorithm. Peterson and Decker's algorithm is a somewhat very famous log-free let's say, software log algorithm. And I think your textbook does not have a much detail on them, but I will give a. So if you check on the Wikipedia page for these two algorithms, you can get more. You can have a better understanding on them. I highly recommend you to read on that. Then how actually log is implemented and used with a little help from computer architecture. Computer architecture provide atomic instruction. I told you, we learned that every instruction is atomic, right? Yeah, every instruction is atomic. But this one is especially referred as atomic instruction because it encompasses multiple steps into single instruction, such that they can be executed atomically. So this is a specially designed instruction for providing synchronization of a multiple thread. So hardware here means computer architecture provide, supports. I think the English here is not good. Support checking and setting of a variable to be executed atomically at a single instruction. I will revise this sentence and update the slide and share it among you. So you can think of the architecture provides some instruction that are specially designed, and once you look into semantic of that instruction, you see that read and write happen at the same time. So that read and write are guaranteed to execute atomically. Some special instructions are provided for most of the computer architecture. There are various forms of such implementation, and test and set is one of standard way of one of a very typical example of atomic instruction. Check this one. Note these codes are pseudocodes for describing the behavior of the computer architecture. It doesn't mean that test and set is translated into these instructions. Check this one. It receive a pointer. It receive the address of a variable, and then also it receive a value. So it look like ordinary writing instruction. Write this value on this address. This look pretty much the same as a writing instruction. So what it actually does is pretty much the same. It writes the new value on PTR or the PTR. So it's a kind of a writing or setting. But at the same time, what it does is that it retrieves the existing value that is placed on the address and keep it and return it. So it's a writing, but it have a return value. And once you check the return value says the old value on that memory. So testing means reading, and setting here means writing. Reading and writing happen at the same time. That is what test and set instruction does. So it provides a mutual exclusion of the two instructions, only read and write, but it guarantees atomic instruction of these two instructions basically by utilizing these atomicity. We can implement the locking, and by using locking, we can implement a higher level mutual exclusion. That is something interesting point. So let's read on this implementation of log and unlock. This is actually one valid implementation. And I know that for many computer systems, psled library, once you check on their log and unlock operations definition, then you'll see the similar code. Initially, it have not initially. For data structure perspective, log variable have a single flat variable. So far, it's all right. And then initially, Yeah, for initialization step in make a lock flag 0. 0 means available. And at the lock, what it does is that it utilizes this test and set instruction, and what? It updates lock variable into 1, lock flag into 1. So if it is a log operation, they want to acquire, if the log is available, they want to acquire it. So they want to write the flag into a 1. So writing will happen, but at the same time, the old value, previous value, or I say the current value, right before this instruction to be executed, will be returned. So if the current value, if the current value is a 1 and it asks to update it into a 1, that what? Yeah, the log is already acquired, so we cannot move on to hold this log. So it'll wait it. This thread should be blocked. This thread should be blocked. So it cannot escape from the while loop. But what if this instruction applied writing on the flag, but and the return value of this instruction is 0. Then what? Lock variable, flag of the lock variable used to be 0. So the current thread is reading lock flag 0, and at the same time, lock variable is turning to 1. Yeah, that's the situation. That's what we need to, that's what we want to achieve for log operation. So if that happens, the loop will be escaped and moving on. And the unlock operation is very trivial. It just to say that lock flag is a 0. Make sense? Okay, good. Have any questions so far? So this type of the log operation is often called as the spin lock. Spin lock. We say that this library implements the spin lock with the atomic instruction. So atomic instruction means test and set. Similarly, test and set, the famous atomic instruction is test and set, and very similar yet different instruction is what called it as a compare and swap. Compare and swap. And there are various versions of them. And depending on the computer architecture, the instruction that it provides are different. And some architecture provide a rich set of atomic instruction that can be utilized for different reasons. So for example, atomic increments are also widely, many computer architecture provide atomic increment instruction, which increment the value atomically. I think I already show you kind of a demo for the counter example. And yeah, and spin locking means that here it have a loop. It implements the blocking behavior by looping, right? It just continue looping, continue checking whether the condition is satisfied or not. So here blocking is implemented by spinning on condition checking. So this way of the implementation is called the spin lock, because the locking operation keeps checking on the lock variable until it finds condition to be satisfied. There are other implementation exists. There is. Spinning is a somewhat inefficient because, even before, if this thread track the log is currently unavailable and get occupied, is acquired one, it'll be better this thread to be get blocked, not spinning on the variable, but it's just going into the waiting status. as if it is doing the IO for it do the IO operation for external devices. It'll be better for put this thread to be waiting status. However, yeah, if it's just doing spinning in this way, the thread will be remained as an active status or running status. So it'll take some CPU time for spinning, but that spinning will be just wasted, right? Because yeah, no matter how much it spins on there, it does not make a progress, because it make a progress only when the other thread gets to be executed. So spinning is not an efficient way for implementing blocking behavior of a log operation. But still, this is widely used because putting a thread to the waiting status is also a costly operation, because it involves data structure updates and many scheduling queue updates and so forth. So for simple cases, spinning will provide a better efficiency. And this is easy to implement. And I told you that this can be implemented in this way, even as a user level library. So spin locking is also used. And we will check on another synchronization mechanism called semaphore. And once we check the semaphore, we will have a more, a semaphore is usually implemented not as a spin locking, but by using waiting queue. So at there, we will see a different way for implementing blocking behavior. Okay. So basically, we now have understanding how log operation is implemented correctly. Okay. So our discussion was on locking. And by using locking, we can achieve atomicity, enforcement of the atomicity to our critical section. That's kind of good. But if you really work on implementing multi-threading, you need another need for synchronization. That is to enforce ordering between threads. Mutual exclusion is restricting the interference among the threads, but it does not enforce ordering. So sometimes you want to have a thread number 1 and thread number 2 working on the same variable. For instance, in here, thread number 1 is to initialize this variable, and thread number 2 retrieve the data from this variable. So in such a case is what? You always want this operation of the thread number 1. I just called it this one as operation number 1, and this one is operation number 2. You always want to enforce operation number 1 should be executed earlier than operation number 2 of a thread number 2. How do you enforce that? By providing locking. No, yeah, it shouldn't happen in that way, right? Even though you put a lock in front of those 2 instructions, yeah, they cannot be executed at the same time, but locking does not mean to enforce ordering among them. Lock is to avoid entering critical section at the same time, but it does not implement enforcing thread ordering. So we need to have a different mechanism. And there are different solutions for this problem. And one famous synchronization primitive used for enforcing the ordering is conditional variable. And sometimes it is referred as a wait and notify. Wait and notify and conditional variables are 2 different concepts, but I think your textbook also address them as the same thing. Yeah, they look pretty much similar. So I just introduce them at the same time. Wait and notify is like this one. We here put an operation wait m, for instance, wait m, and it means that it should wait on some channel m, which I say it's a channel. It's just to wait some channel m. You can also regard it as a receive. it says that I need to receive a message from the channel M. And before receiving the message, the control cannot move on. Control cannot pass on to the next instruction. That's what waiting means. And then what? At here, so even if the thread number 2 is the first executed, then thread number 1, it'll block at waiting operation because initially there is no message given. And then thread number 1 execute this code and give a notification, notify M. Notify M. Then what it means is it send the message. Send the message via channel M. Then it give a signal. Then only when, then this signal will be received by thread number 2. So thread number 2 can continue its execution. In this way, we can program thread ordering across threads. Okay, and detailed use cases and also the case that these are used for implementing algorithm will be, you can find some of them from the video tutorial. And also at the next class, I will elaborate it on some log data structure. There, we'll see more details on how to use them to implement some meaningful algorithm. Okay, so here, today's lecture, I introduced you a little more detail about a log operation and how it can be implemented. And also, I briefly introduced about different synchronization mechanism, wait and notify, or conditional variable. These tools are some essential. These tools are somewhat essential synchronization primitive. And with these two mechanisms, we can program most of the concurrent algorithm that exists today. So we need to learn how to use them and how to exercise them in a proper situation in multi-threaded programming. And that topic will be addressed in next class. Okay, have any question? That's it for today. So if you have a question, I'm welcome to answer your questions.